let's resume our discussion on power series. Please remember that there are three important topics to cover. Number one, the interval of convergence. Number two, the term-by-term differentiation and integration. Number three, power series expansion formulae that are derived from geometric series formula this time. In the first video clip, we talked about the definition of the power series and some lingos. And then we talked about the domain of the power series function, or in other words, the interval of convergence. We did some computation problems, and the typical tools to calculate the interval of convergence was the ratio test. Sometimes we can use the root test, but that's rare. Ratio test is usually the way to go. Topic number two was calculus of power series, which was covered in the second video clip, by the way. The derivative and antiderivative formulae are here, and they share the same radius of convergence, same interior and exterior of the interval of convergence. At the end point, you'll have to test them manually anyway, but here's a nice insight. If you take the derivative, the coefficients tends to get bigger, so you're going to end up losing some convergence at the end point. How about the antiderivative? It's the other way around. The coefficients get smaller, so you're going to end up gaining some convergence at the end point. That's a nice insight. And then we talked about power series expansion derived from the geometric series formula. So here it is. Geometric series formula. Replace x by negative x, and we have the second formula. From the second formula, take the antiderivative term by term. Then you're going to get the expansion formula for logarithmic function. And from the second formula, if you replace x by x squared and then get the alternating sum of x to the even powers, and then if you take the antiderivative, then you're going to get the arctangent function, the expansion for arctangent function like this. Now, all the way from the start, from the geometric series formula, if you take the derivative, not antiderivative, this time derivative, then you're going to get the fifth formula. Replacing x by negative x, you're going to get the sixth formula, formula number 6. Or you can actually take the derivative from here, and then, oh, that's a bit complicated. You'll have to consider negative sign, so never mind about that. It's going to be easier to derive the sixth formula from the fifth formula. Okay, that was a quick review on two prior video clips, and let's move on to some examples. How about a problem like this one? This is really standard problem, 1 over 1 plus something. So this is going to be just immediate application of the formula number 2, which I rewrite over here. And here, just replace x by 9x squared, and we end up with, well, this, and it can simplify it into something like this. And that's it. How about the interval of convergence? Well, did we just replace x by 9x squared? So 9x squared will go over here, generating this inequality. And then 9x squared is always non-negative, so left-hand side doesn't really matter. 9x squared is less than 1. Taking plus or minus square root, we get 3x's between negative 1 and positive 1, eventually generating this interval of convergence. You can actually check the answer through running these Mathematica programs here. Mathematica commands rather, not really program. How about the next problem? This one is going to be pretty much the same as a matter of fact, because we have a linear function in denominator, and also the middle sign is plus. But there's a bit of a problem. Instead of 1 plus something, we have something different. How do we work it out? Well, we use very typical trick that you should remember. Well, this is a formula we're going to be using, formula number 2. And the first manipulation is to change the order of addition. 3x plus 2 becomes 2 plus 3x. No big deal, just ascending order. And then here is the typical trick that you have to remember. You have to make this one into 1. How do you make 2 into 1? By dividing by 2. So divide everything by 2. Divide by 2 and then divide by 2. The numerator does not really matter too much because you can multiply afterwards. So what we have, 1 over 1 plus 3/2 of x. And that 3/2 of x will replace x in the previous formula. Basically what happens is this one will be replaced by 3/2 of x. And that's what this formula is all about. After that, a little bit of simplification. X times, in the numerator, x times x to the nth power, so we have x to the n plus first power. And then in denominator, 2 times 2 to the nth power, so we have 2 to the n plus first power. What's left will be negative 3 to the nth power. How about the interval of convergence? Didn't we just replace x by 3/2 of x? Well, that's about it. So we end up with x is between negative 2/3 and positive 2/3. You can easily check by running this mathematical command. How about something like this problem? Well, we have complete square in denominator, so this must be formula number 5 in this box. And let's rewrite it over here. And let me expand the font. The typical deal here again, this 3 doesn't look too good, so I want to change it into 1. How do I do that? Divide it by 3. If I'm dividing this one by 3, I have to divide 3 from everything. So divide 3 from this one. And because I divided 3 from inside of the square, outside I'll have to divide by 9. So we end up with something like this. X cubed over 3 squared is no big deal because you can always multiply it later. And the series expansion for 1 over 1 minus x over 3 squared will be just this one, where x is replaced by x over 3. So that's what happens. This x is replaced by x over 3. After that, just a little bit of simplification. X cubed times x to the n minus first power. So we have x to the n plus second power. 3 squared times 3 to the n minus first power. So we have 3 to the n plus first power. And numerator remains as n. The interval of convergence, again the same deal. Because I replace x by x over 3, we have to do the same thing for the interval, and we end up with the open interval negative 3 to 3. You can easily check that by running this mathematical command. And please note that negative 3 plus x squared is the same as 3 minus x total quantity squared. How about this problem here? Very similar. We have log of 1 plus x formula here. So this must have something to do with that. And somehow you have to change 5 into 1. How do we do that? Just like previous 2 problems. Divide by 5. But that's a little bit trickier this time because we don't have fraction. We have to apply a log rule. And here it is. Factor 5 out and divide by 5. So we end up with 1 plus x over 5. And then we apply the log rule. Log of 5 plus log of 1 plus x over 5. And then everything is easy. Just replace x by x over 5 in this formula over here, all these. And that's what you're going to get in the second line. And sigma notation of that will be the third line. And then after some simplification, we get the fourth line. How about the interval of convergence? From here, all we have to do is replace x by x over 5. Eventually, you're going to get this. X is greater than 5, but less than or equal to positive 5. X is greater than negative 5, but less than or equal to positive 5. You can check your answer by running a Mathematica command like this, and it checks out. Problem number 4, or problem E, is left to the students. It's a bit more challenging, but you can handle it. The hint is to complete the square. Because we have a trinomial, our formula will not apply directly. If you go back to these, we only need 2 terms there. So if you use complete square, then you're going to get something plus a sum bunch squared, kind of like that. I think I gave too much hint. Okay, now let's work on some kind of problems that you have to find out the value of an infinite sum through power series method. This is a bit too trivial. Just go over to the box, the table, and then which one is the alternating series with denominator n, and clearly we have a log function, and we don't have x to the nth power there, no power, so this will be just 1 to the nth power, and you're going to end up with log of 1 plus 1 or log of 2. Too simple. This one is a bit better, a little bit more challenging, but still relatively easy. We have 2 to the nth power in denominator, which means we are looking at 1/2 to the nth power. So we are plugging in x equals 1/2. Now, to which formula? Which formula has n in numerator? Well, here it is. So here, plug in x equals 1/2, then you're going to get, well, 1/2 to the n minus first power. That's not what we have. We want 1/2 to the nth power, not n minus first power. So we need a little bit of algebraic manipulation, basically just multiplying by x. From here, multiply by x, generating n, x to the nth power. Now plugging in x equals to 2, x equals 1/2, excuse me, the answer turns out to be 2. You can check your answer by running Mathematica command like this. I'm going to leave the other 2 problems to students here. And alternating series with denominator is 2n plus 1, all the odd numbers. So obviously, that problem must have something to do with arctangent function. Okay, that's where I'm going to stop. Alright. The final types of problems are integral computation coming from the power series expansion. How about the first problem here? The integral of log of 1 plus x squared dx. If you have just log of 1 plus x, that's easy. You can do it by integration by parts. But this one is very different story. You cannot use substitution. You cannot use integration by parts. You can use power series expansion though. You can start from the expansion of log of 1 plus x, which is given over there, and replace x by x squared. That way you're going to get the second expansion formula there. And then if you take the antiderivative term by term, well, increase the power by 1 and divide, so we end up with this highlighted infinite sum. And that is the infinite series you're looking for, infinite power series you're looking for. How about the interval of convergence? It's going to be -1 to 1, and you'll have to consider the endpoints manually. Plugging in x equals to -1 and plugging in x equals to 1, what do you get? Well, you're going to end up with absolute convergence for both of them, to tell the truth, because if you take absolute value and in that case, everything in numerator will simply become 1, and then you're going to get a series, numerical series, which is asymptotically equivalent to the p series, 1 over n squared. And that's because the denominator has growth order of 2. The detail is still left to the students. Do we have a bit of time to talk about the final problem here? Not much. I'll give you a sketch. we can start from expansion of arctangent function, but x minus arctangent will kill off the first term, and we have all these. And dividing by x cubed will have something like this, and then integrate term by term. Tricky, but you can do it.